So, this is MAT 221. This is section 2.7. We're talking about the derivative as a function. This is Mrs. Johnson. We can estimate the derivative by looking at the slope of the tangent line to the curve at key points. Now, the good idea is to start where the turns are, the minimums and maximums of the function are, those local mins and maxes, where the curve is turning, and we know that the tangent line will be horizontal at those values. And then we usually pick other points on the curve also. I'm going to plot a bunch of points here on the curve. So I just put a bunch of points on the curve. And what you would do is you would space those points throughout the curve and give a good estimate as to what the slope will be. Now the key thing is to look for is possibly look for points of inflection, where we know points of inflection from pre-calculus we know is where the curve is growing or dropping the greatest. And what we would do here is we would sketch tangent lines to the curve. So I would sketch a tangent line to the curve at each one of these points. Here, when x equals perhaps negative 0.5 or negative 0.2, we know that the slope should be negative. So we know that we should plot a point below the x-axis on the derivative curve. Here at the point of inflection, we'll have a positive slope. Looks like this is rising about 1/1. Here we'd put another one. Here the derivative would be negative. Here the derivative would be negative, but less negative as we're coming back toward this horizontal tangent line. Here we'd have a positive slope, then more positive as we move through. If we connected these dots and plotted each one of these points so that the x-coordinate matches the x-coordinate of the original function f of x, but the y-coordinate becomes the slope, whatever the slope of the curve is at that point. Now, if I did this curve, it would look something like this if I repeated that throughout. Now, again, at this point, I just want a general shape of the curve. What's my general shape as I go along? This definitely takes practice, and I'm going to do some more practice with you, especially with some worksheets, so we can take this and really learn how to do this procedure. Here's another one where I'd like you to think about. This is a parabola. This is a quadratic function. Actually, we could come up with the formula of this. This looks like x squared that's got moved down 3. But I want to start with sketching the derivative. What would the sketch of the derivative look like? What we would do is we would start first of all with a point where it looks like I have a horizontal tangent line. So I know the point 0, 0 has to be on the derivative graph, because the derivative when x equals 0 is equal to 0. So that means the point 0, 0 has to be on my derivative graph, my derivative function. Let's pick another point. Sketch the slope of the tangent line there. This one I'm guessing looks like my slope's about -2. And again, I'm just in the ballpark there. It looks like I'm going down 2/1. So I'm going down 2 units and then over 1 unit here when I look at this curve. So I know the point -1, -2 has to be on my derivative curve. I pick another point on the original curve. I sketch the tangent line. I look at its slope. Looks like this slope is about a slope of 2 at the point x equals 1. I put another point on the curve at x equals 2. I sketched my tangent line. This one definitely looks more positive. Looks like I have like a pretty steep slope, maybe 2, 4 is going to go in my derivative curve. And then I'm going to pick another point on the curve, say at -2. I sketch its tangent line to the curve. I definitely have a pretty steep curve there. And then what I do is I take these points that I've now found. Now notice each point is the same x-coordinate, but the y-coordinate is the slope of the curve at that point. Same x-coordinate, slope of the curve at that point. I take them and I sketch those points and I connect the dots. When I do, I get a function that looks something like this. 0, 0, -1, -2, -2, -4, 1, 2, 2, 4, and then I connect those dots. This is a sketch of my derivative curve. Now, we just said a minute ago, it looks like that parabola looked like the function y equals x squared minus 3. Now, if we have an actual formula that we have for the curve, then all we have to do is use the limit definition of the derivative. So I'm going to use this limit definition of the derivative. Remember, the derivative is equal to the limit as h approaches 0 of x plus h, f of x plus h, which is x plus h squared minus 3, because that would be f of x plus h, minus f of x over h. Now remember, I'm just happening to use this function that I have here as my f function. So this portion right here is f of x plus h. This portion right here is f of x. And I put it over h and I subtract them. Now in the last section, we usually put in a number for x, or a we put in here. But now we're finding the general derivative, or the general function that the derivative is going to look like. Now let's do some algebra here. X plus h squared is x squared plus 2xh plus h squared. Minus 3 and then plus 3 would cancel. Then I'd have minus x all over h. X squared and negative x squared will cancel. One of those h's will cancel there also. So I have the limit as h approaches 0 of 2x plus h. As h goes to 0, this limit is equal to 2x. Now wait a second here. The function y equals 2x, if we graphed it, would look something like this. Notice that is exactly what I got in my last expression when I was just sketching the derivative. I got a function that's a linear. So I started with a quadratic and became a linear. By the way, that will always happen when we get to our shortcut rules. Power functions will drop down a power. So notice when I do the limit definition of the derivative, I get the general derivative of f prime of x is equal to 2x. The function 2x looks like this, which is our derivative function. Now I can find the derivative at any point I want to of the function by simply putting in whatever my x value happens to be. All right, let's talk about differentiability. We talked a little bit about this already when we looked at the piecewise function in the very beginning when we were sketching that. And we saw when we had sharp corners on the graph that the right-hand derivative and the left-hand derivative were not agreeing. Therefore, we said that the derivative did not exist. So a function is considered differentiable if the derivative exists at every point. We said that the right-hand and left-handed derivatives may be defined at any point in the function's domain. The usual relationship between one-sided and two-sided limits holds for derivatives here too. We can conclude that a function has a two-sided derivative at a point if and only if the function's right-hand and left-hand derivatives are defined and equal the same thing. In other words, the slope from one side has to equal the slope from the other side as we're getting toward that particular point. That said, what happens and what we discover and what Leibniz and Newton discovered is in order for something to be differentiable, a function must be continuous and smooth. And there are 4 places where the derivative will fail to exist. When we're looking at a curve, and if we see a sharp corner as we did on the piecewise function, we can conclude that the derivative will not exist. And that's pretty easy to see. You can see the slope on one side will always be negative. the slope on the other side will always be positive, and they will never agree. When we have a curve and we're curving into a vertex point or a turning point, then the tangent line gradually does curve to 0. Here, the tangent line will never curve, it's just staying negative and then staying positive. So anytime we have a sharp corner on the graph, we say the derivative does not exist. All right, that said, we also, when we have a cusp, now what is a cusp? A cusp is very similar to a sharp corner. Matter of fact, they look a lot alike. It's just that the curve is curving into that cusp and curving out of that cusp. So whenever we have a cusp on a curve, again, the derivative will fail to exist at the cusp because the right and left-hand derivatives will not agree. The fourth place where we will never have a derivative is when we have a vertical tangent line. Now we know from way back when that a vertical line has no slope. And because the derivative of a curve is the slope, if the curve goes vertical at an instant, for instance, in this case at x equals 0, the curve goes vertical and the tangent line would be vertical, the tangent line would have no slope. Therefore, the derivative would not exist because we don't have a slope. And then lastly, the derivative fails to exist anytime I have any type of discontinuity. Jump discontinuity, removable discontinuity, infinite discontinuity, any type of discontinuity, I will not have a derivative on my graph. So we really need to remember these 4 places. Whenever I see a graph and I have a sharp corner, a cusp, a vertical tangent, or any type of discontinuity, I know that the derivative will not exist at those points. Here's an example of the one that we did with absolute value. If I were to actually show you this is the proof that the left and right hand derivatives actually don't agree here, if I use the limit definition of the derivative on this formula, I would get -1. If I did the right-handed derivative on here, I would get +1. And those derivatives will never equal at x equals 0. Therefore, the function will not have a derivative at x equals 0. So, since these limits are different, the derivative at 0 would not exist. Thus, f is differentiable everywhere except at x equals 0. So the formula for the piecewise function, which is actually the absolute value function, where this is the output is equal to 1 for everywhere greater than 1, -1 for every x less than 0, the derivative would look something like this. I would have a -1 derivative, then no derivative. I would have a hole there, and then I would have a derivative of 1 from that point on. This is the derivative graph for the absolute value function. So both continuity and differentiability are desirable properties for a function to have. This following theorem shows how these properties are related. It says, if f has a derivative at x equals a, then f must be continuous at x equals a. Well, we just said that if f is not continuous, then I won't have a derivative. So if I have a derivative, then I must be continuous. Since a function must be continuous to have a derivative, then it has to have a derivative to be continuous. Then it is continuous. However, the converse of this is not necessarily true. That is, there are functions that are continuous, but not differentiable. For instance, the function that you see up here, this function is continuous everywhere, but at this point right here, I have a vertical tangent line, so there's no derivative there. So look at the difference between the two statements. If I have a derivative at a point, then I must be continuous. But if I'm not continuous, it doesn't guarantee that I'm differentiable.